Let's use vectors to solve a couple problems with components and Newton's laws, kind of combining a little bit here. So we have a cannon firing a ball 90 meters per second at an angle of 40 degrees with respect to the horizontal. Let's figure out the horizontal and vertical components of the velocity. Okay, there's the velocity. What are the horizontal and verticals? So we have the reference lines drawn here. If we were doing this graphically, here's the horizontal velocity, and then there's the vertical velocity, just like we've done in the past. So we can measure that with a scale of 1 centimeter is 20 meters per second. That's how I originally did this. 3.5 centimeters on the horizontal times 20 meters per second per centimeter gives us 70 meters per second. For the vertical, we do the same thing. 2.9 centimeters unscaled then is 58 meters per second. We could check this with trig. Since this is right angle trig, it really does lend itself to using it. So sine of 40 is the sine of this angle is opposite v vertical over hypotenuse, the original speed, and that's VV over 90, so VV is 90 sine of 40, which is 58 meters per second. Yay! How about the horizontal? Horizontal, 90 cosine of 40, which is 69. So we see we have a validation there for our answers. Let's do another problem. We got a cart, 10 kilograms. We're going to apply 100 Newton force, but not at this funny, well, not in the direction it's going to move. All right, it's going to accelerate horizontally to the right. What is that acceleration with this force applied? Does it matter that we applied the force at a funny angle? Well, it actually does, because not all of this force is used in accelerating the cart. In fact, you may be able to recognize that it's the horizontal force that causes it to accelerate. Remember, the net force and the acceleration are in the same direction. So if this is the acceleration direction, it's also the net force direction, and the net force is the horizontal. I don't have all the forces shown on here. This is a 27-degree angle, by the way. There is a vertical component, and that vertical component does not contribute to the acceleration. It's perpendicular to it. Horizontal force, 4.5 centimeters, based on the measurement. Unscaled, 90 newtons. Then the acceleration is F net over m, 90 over 10, 9 meters per second squared. With trig, we can validate the horizontal, 100 cosine of 27, 89 newtons. So I consider it validated. Okay, we're going to do a lawnmower problem. But the problem is just to find the normal force acting on the lawnmower. So here's all the data. You're pushing on this handle, which is 40 degrees from the horizontal, with 150 Newton force. The lawnmower is 20 kilograms, and it's going to move along the ground. And you got to figure out the normal force. And you may think right away, well, gee, it's on a flat surface, so of course, just the weight of this, gravity pressing it into the ground pushes back up with a force equal to its weight. Turns out that's not going to be the case. So unfortunately, you have to kind of analyze the situation, think through it. I should say fortunately. It's fun. This really isn't all that difficult, as I think you'll see. I'm going to start by putting this force, applied force, here, because I like to have the tail of my forces basically in close proximity to or attached to the object in question. So there it is. Now this has a horizontal component and a vertical component. You may be seeing the issue already with the normal force. If not, you will. So here is the rest of the story, the weight of the lawnmower and the normal force. Now you might notice I drew the normal force a different length, and we'll see why that is. So little trig analysis on this. Sine of 40, F vertical over 150, so the vertical force is 150 sine of 40, which is 96 newtons. So this is 96 newtons. By the way, this force, 20 times, if you just call G10, we got 200 newtons there. So 96 newtons on the vertical force that we're applying. The sum of the forces in the y direction. Now you can write down the answer, the numerical answer, real easily by recognizing that there is no change in position of the lawnmower vertically. In other words, it's not moving vertically. More specifically, it's not accelerating vertically. So we know it's 0. That means that all those forces in the y direction have to cancel. Well, let's do a free body diagram. Starting here, we have the weight and we have the force vertical from applied. Now you're probably seeing why the normal force is not equal to the weight. Well, we also have the horizontal component, and there's the normal. What is the normal? The normal is the weight plus the vertical force. It's the combined effect of both of them. Because when you push down on this, you're pushing down vertically with this force, which makes the ground shove up that much harder because the ground doesn't want to give way and open up its big throat, so to speak. In other words, you're not going to shove it through the ground, accelerate it into the ground. So the ground just pushes up with the force that it needs. So here's the answer. Normal is mg plus f vertical, 200 plus 96, and out pops the answer. So notice that we always have to consider the entire situation before we can jump to quick conclusions. Like, for instance, the lawnmower is on a flat surface, therefore its normal is equal to the weight. Well, if you let go of it, that would be the case. But you start adding another force, like this applied, and it obviously changed the situation. So I hope you're starting to recognize the value of vectors as applied to Newton's laws problems. And you will have plenty of opportunity to continue your development of that useful skill. See you next time.